This is an example of a finite horizon bilateral bargaining model developed by Stahl. It's actually outlined in Appendix A of our textbook, Mascolel, in Chapter 9. And in this model, two players, player 1 and player 2, have to bargain to determine the split of V dollars. So V dollars are being bargained over. And the rules are that the game begins in period 1. So at t=1, player 1 makes an offer of x to player 2. Player 1 makes an offer, and player 2 can either accept or reject the offer. By the way, the offer here is going to be x, and x is a number between 0 and v. If player 2 has rejected, now we move to period 2, and player 2 makes a counter offer. Player 2 can offer, again, a number between 0 and v. And player 1 can either accept or reject. And we are going to continue like this. Now we move to t=3, and the game continues until period t is reached. So t is the end of the game. And in period t, if there's no agreement, then the players receive nothing. So, as it turns out, there is a unique subgame perfect Nash equilibrium in this game, and to see this we have to look at the last node and apply backward induction. So at the last node, we are looking at time t, and if t is odd, we know that player 1 is making a decision here, and player 2 can either reject player 1's offer or accept it. If the offer is rejected, the game ends without any agreement having been reached, so the players get nothing. If player 2 accepts the offer, then player 2 gets whatever was offered, and player 1 gets v minus whatever was offered. And the key thing to see here is that player 1 really has no incentive to be generous with player 2, because player 2's bargaining position is not that strong, given that player 2 will get nothing if he rejects the offer. So player 1 could actually offer something very, very small to player 2, something like 0.001, right? A positive number, but very, very tiny. And player 2 would be better off to accept the offer than to reject it. So at the limit, we're looking at an offer of 0, in which case player 1 actually gets v as a payoff. This is a little bit hard to see at first, because you might think that, hey, wouldn't player 2 out of spite simply reject the offer so that instead of getting v, player 1 gets nothing? So player 1 would be in some sense punished for being so cheap or making such a bad offer to player 2. But really, the idea here is simply to view that this is at the limit, and at the limit, player 1 can simply offer nothing. And player 2 would have no reason to reject this. So, moving back to t-1. Now player 2 is making the offer. Player 1 can reject the offer, in which case we move on to the last node. Player 1 can actually also accept the offer. What are the payoffs? What kind of offer does player 2 need to make in order for player 1 to have an incentive to accept? Player 1 needs to be made at least as well off as it would be if it were to reject the offer and get the payoff of period t. The payoff is v. So player 1 needs to get v, except that we're now one period before, so this needs to be discounted back to by one period. This is the discount rate for player 1. We can assume that both players have the same discount rate or different discount rate. Just to make this simpler, I'll just assume it's the same discount rate for both. So if that's the offer made to player 1, then player 2 simply gets V minus this offer. And now we can move to period T minus 2. Now we know that player 1 is making the offer, which player 2 can either reject, in which case we move to period T minus 1, or accept. What does player 1 need to offer to player 2 in order for player 2 to accept? Well, player 2 needs to be made at least as well off as it would be in the next period. So player 2 needs to get V minus V times delta, but this needs again to be discounted by 1 period. So player 2 needs to get V delta minus V delta squared. And player 1 gets V minus this amount. So minus V delta plus V delta squared. And we can continue going like this. Now we want to be able to express all of these payoffs in terms of their present value in period 1 in order to be able to compare everything. So expressed in terms of their present value, the payoffs become, I'm changing color so that you can see better. So in period T, we have V times delta to the power of T minus 1. We're discounting back to the first period, and 0. In period T minus 1, we have V times delta to the power of T minus 2. And we can, of course, simply write V times delta T minus 1. The payoff for player 2 is V times delta T minus 1 minus V times delta T minus 2. Okay. Now looking at period T minus 2, we multiply everything by delta to the power of T minus 3 to go back to period 1. So we have V delta T minus 3 minus V delta T minus 2 plus V delta to the power of T minus 1. And then for player 2, we have V delta T minus 2 minus V delta T minus 1. Okay, this is a little bit involved, but you get the picture. Now the key thing here to focus on is simply to look at the payoff for player 1 in the long run, what that payoff looks like. And of course we can factorize by V, since all the terms contain V. Let me just write that on the next slide. Right, so if we were just looking at 3 periods, something simple, the payoff for player 1 would simply be V. I just factorize everything by V. So this I've already derived. Okay. And, you know, if T is equal to 3, then you could see that this first term here, this is simply going to be 1. And in fact, the first term out of every such discounted payoff will always be 1. So what I'm really getting is V times 1 minus delta T minus 2 plus delta T minus 1. And we can rewrite this as simply v times 1 minus delta plus delta square minus plus delta t minus 1. This is just for a general expression. Now, as the limit of this expression, as t goes to infinity, we're looking at larger and larger number of periods in this. The limit of this expression is simply v over 1 plus delta. This is for player 1. And for player 2, so this is the payoff for player 1, and then the payoff for player 2 is simply v minus the payoff for player 1. This is also equal to delta v over 1 plus delta. So these are what the player 1 and players 2 payoffs converge when the number of periods grows larger and larger. So these are the solutions, the Nash equilibrium of this particular game.